Hello, everyone. Welcome to the afternoon session. As we are very much excited to start with, we are going ahead with the keynote lectures from our Nobel laureates. We are running on a very tight schedule here, so we'll quickly get started. And the presenter will be leaving some options to ask you questions in between. Before anything else comes up, I think we can get started up. For the first session of this today, we have Dr. William Phillips with Nobel Prize in Physics in 1997 for his work on developments of methods to cool and trap atoms with laser light. He should be on the big screen in just a moment. Great. Let's welcome Dr. William again. William, you are on the big screen.
Thank you very much. It's a pleasure to be with you today and talk to you about the quantum reform of the modern metric system. I'm from an institute called the National Institute of Standards and Technology. This is the metrology laboratory of the United States, and most major industrial countries have such a metrology laboratory. In the UK, it's the National Physical Laboratory. And one of the things that we do is maintain the standards of measurement for the nation and internationally. I want to encourage you to think about questions. We're going to stop several times during the lecture to receive your questions live. And if you're in Zoom, please put your questions into the Q&A. So, what's the big deal about the metric system? Why do we care so much about measurement? Well, science is about what you can measure. At least that's what Lord Kelvin said. He said, when you can measure what you're speaking about and express it in numbers, you know something about it. Now, you may argue with his opinion about things that you cannot measure, but when it comes to science, we generally measure things. And so if you measure things, then you have to have units in which to measure them. And as an international scientific community, we have agreed to use the metric system of units, which is formally known as the International System of Units, or the SI. The SI is a system of units that is based on 7 what we call base units: the kilogram, the meter, the second, the ampere, the Kelvin, unit of temperature, the mole, the unit of substance, and the candela, the unit of luminous intensity. This metric system came into being with the French Revolution at the end of the 18th century. And on the 20th of May, 2019, just a few years ago, World Metrology Day, we had the greatest revolution in measurement units since the French Revolution. Excuse me. Now, what was the nature of this revolution? This reform means that all of the base units of the International System of Units are now defined by fixing the values of constants of nature, constants that are often quantum constants. In order, sorry about that, it's a little early for me. It's just 7 o'clock in the morning, and I guess my voice hasn't acclimated itself yet. To see how this can be done, that is, how we can define units by defining or fixing a value of a constant of nature, I'd like to review how this was done at an earlier time for the unit of time, which started as a classical unit and has now become a quantum one. And so, with apologies to Stephen Hawking, the late, great Stephen Hawking, I'm going to attempt to bring you my version of a brief history of time. Since we have had seconds, a second has been defined as being a fraction of a day. There's 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day. And so a second is 1 day divided by 86,400. Now, the trouble with this definition is that since around the year 1900, we have known, excuse me, that the length of the day changes. And that's not tolerable when you're making really precise measurements. We need a definition of time that is something that we can count on as being constant. And the quantum definition of time something that was adopted in 1967 is that the second is the duration of a certain number of periods, some 9 billion periods of the radiation corresponding to the transition between two energy levels in the cesium atom. Here's a picture of the first cesium clock. It was made in the United Kingdom. I really apologize for my voice. I don't know why I'm having so much trouble. And I also apologize that I can't mute myself when I'm in sharing mode. But anyway, let's hope that this stays all right. Here's a picture of the first cesium clock, which was operated in 1955 here in the United Kingdom at the National Physical Laboratory. And this clock, because it relies on an atomic property, the property of the atom of cesium, the energy levels of the cesium atom, we don't have to worry about it changing with time. But with time, it's gotten better and better. When it was first operated, this clock was good to about a part in 10 to the 11th, which is amazingly good. But over time, by the time we reached the 1990s, this clock was better than a part in 10 to the 14. But the performance of this clock and other clocks like it was stalled at about a part in 10 to the 14 because of the fact that the cesium atoms are moving so fast. These cesium atoms are in a gas, and any gas at any non-zero temperature, and by zero temperature, I mean zero absolute on the Kelvin scale, where absolute zero is the coldest temperature you could possibly have. Room temperature is about 300 degrees on that scale. All atoms are in constant thermal motion. And the cesium atoms, moving at over 100 meters per second, were moving so fast that it made it essentially impossible to make these clocks better than a part in 10 to the 14. This is where laser cooling came in. As you heard in the introduction, I shared the Nobel Prize in 1997 for laser cooling. And our group at NIST developed many of the techniques for laser cooling. And applying those techniques to atomic clocks made it possible for those clocks to achieve an accuracy today that's a few parts in 10 to the 16. This is an incredibly accurate measurement of time. It's the most accurately measured quantity in the International System of Units, in the modern metric system. And the point here is the one that I want to emphasize very strongly. We went from something that was totally arbitrary, the rotation of the Earth, to something that is based on a constant of nature, the energy levels of an atom. And this is something that is determined by quantum mechanics. This also realizes a kind of a dream that was had by some of the physicists of the 19th century, like Kelvin and Maxwell. They believed that the properties of atoms were something that were absolutely immutable, unchanging in time, and completely consistent from one atom to another. This was at a time when a lot of people didn't even believe in atoms, yet Kelvin and Maxwell did, and they also believed in the usefulness of atoms as standards, as indicated here, that they thought that you should use atoms as a standard of time, and as we'll see, as a standard of length. These incredibly accurate quantum-based clocks are not just philosophically satisfying in the way that Kelvin and Maxwell were thinking, but they're also things that have led to commercial application. The satellite navigation system, the sort of thing that we all use to find our way from one place to another, the satellites that make this possible each have on board several atomic clocks. And these are the things that allow us to navigate using our smartphones or our standalone GPS receivers. That system of satellite navigation depends crucially on understanding Einstein's theory of gravity. When Einstein came up with this theory in about 1915, it was considered to be so arcane that it was reported that only 3 people in the world understood Einstein's theory. Today, if the engineers who designed the global positioning system, the satellite navigation system, had not taken into account Einstein's theory, that navigation system would be wrong by kilometers within a day, whereas we use it routinely to navigate ourselves accurately to a few meters, and often much better than that. So let's stop for a moment here and see if anyone has any questions about time. And I've offered a few possibilities for questions that you might be interested in, but I'd much rather have the questions that have arisen in your own minds. So, do we have any questions from the chat or locally? We can go on. I can see Aaron poking his head into the screen from time to time. So, is there nothing?
We can go ahead for now.
Okay, okay, let's keep going then. So, even better, I would like to bring you a short history of length. Historically, time was important, but length was even more important because of the fact that it had to do with commerce and with construction. Things were sold in terms of how long they were. Fabric, for example. Buildings were built based on measurements of length. And the story that I'm going to tell you about length is even more beautiful than the one about time. The earliest approach to length was based on the size of the human body. A foot was a foot. A yard was the span of one arm. A fathom was the wingspan of a person. The cubit was the distance between the elbow and the fingertips. This was really convenient because you always had your standards with you. The problem was that it was inconsistent because everybody's body is a little bit different. Well, one approach, and the approach the ancient Egyptians took, for example, was to base the unit on the size of the pharaoh's forearm. This was called the royal cubit. But they also realized that it was inconvenient to always refer to the pharaoh because he wasn't around. So they made a standard, a granite rod that was the primary cubit for Egypt. And there's a picture of one end of that rod. And it was used, for example, in the building of the pyramids. That idea of making an artifact a physical standard for length was something that was used in much more modern times throughout the Middle Ages in Europe. There were standards that were often fixed into the walls of buildings. Here is the standard fathom in the city hall in the city of Regensburg. The trouble is that while everyone in the city could come and use this standard, if you were to venture outside into surrounding Bavaria, there would be different standards. So at the time of the French Revolution, the French revolutionaries figured they wanted to change this. They wanted to make something that would be useful and standard for everyone. And so they introduced a new unit of measure, which was called the meter. This is why we call it the metric system. And the meter was defined to be 1/10,000,000th of the distance between the North Pole and the equator along a meridian that runs through Paris. Now, in order to find out just how long that was, they sent out surveyors to survey the Earth, to survey the distance between Barcelona in Spain and Dunkirk in England. And the idea was to create a system of units that was good for all time and for all people. This was their dream, and they in fact cast a medal, which you see here, that shows a mythological creature measuring the earth, because that is what in fact they did as surveyors. They measured the earth. It took them years to do it, and when they came back to Paris with their new measurement of what this new unit of measure was, the meter, they realized that they couldn't be measuring the earth all the time because it took several years to do it. And so they did the same thing that the ancient Egyptians did. They made an artifact. And this is a picture of the meter of the archives. This became, in 1799, the year 1799, this became the standard of length the unit, the meter, for the country of France, very much in the spirit of the ancient Egyptian stone artifact. In 1875, later in the 19th century, the countries of the world got together and agreed by international treaty to adopt the metric system. And they also agreed to make a new artifact standard. This is called the International Prototype Meter, and it defined the meter to be the distance between two scratches on this platinum iridium bar that was made to be as close as they could make it possibly to the old meter of the archives. So this became the standard of length for the entire world, according to the agreement in 1875, and this meter was made a few years later. But this was the late 19th century. Physicists in France and in England and elsewhere had discovered that light, which Newton thought was a stream of particles, that light was actually a wave. And that meant that they could use the wavelength of light as a standard of length, using instruments called interferometers, a cartoon of which is shown here. They could interfere different light waves to produce places where there was more light and places where there was less light, depending upon whether the two waves had the crests of the waves match up or the crests and the troughs of the waves cancel each other out. This kind of an interferometer, the one that's shown here in cartoon form, was invented by a guy named Michelson, who also measured the speed of light. This interferometer was so sensitive that if you were to move this movable mirror by just 1/4 of a wavelength of light, and one wavelength of light is less than 1/millionth of a meter. If you change it by just 1/4 of a wavelength, you change the interference pattern such that this central spot turns from being dark to being light. The scratch on the meter bar is about 20 millionths of a meter wide, 20 microns. We can measure to a tiny fraction of a millionth of a meter using an interferometer. And so people started to use interferometers as a kind of de facto standard. It wasn't the legal standard of length. The legal standard of length was the distance between these two scratches. But the technology had advanced to the point that it was possible to make length measurements that were better than what the very definition of length was. And so people were, again, doing what Kelvin and Maxwell had said. Maxwell said that if you wanted a standard of length, you should use the wavelength of light. He sort of joked that if you wanted your measurements to last longer than the Earth, then you shouldn't use the Earth as a standard. Of course, it was a joke, but he did understand the basic idea that using the wavelength of light would be the thing to do. But it took until the middle of the 20th century before the definition was changed, before the technology that allowed the incredibly accurate measurement of length using the wavelength of light, before that became the legal definition. But 1960 was the year in which the laser was invented, and soon laser light superseded the light from this krypton lamp in terms of its purity and the constancy of its wavelength. Here's a picture of a laser that was locked to the wavelength of a particular transition in molecular iodine. So this is doing just what Maxwell thought should be done, to use something at the level of atoms and molecules to define what we mean by length. So people started to use these lasers as the standard of length. It was not, again, the legal definition of length. The legal definition of length was based on this krypton lamp. But these lasers were better, and people were using them as de facto length standards. So once again, we had a situation where the technology had outrun the definition. And so it appeared that you would need to have, again, a new definition for the meter. And the obvious thing to do would have been to define the meter to be the wavelength of light coming out of a laser like this one. But fortunately, they did not make the obvious choice. They made a beautiful choice, a brilliant choice. They defined the speed of light. The new definition of the meter was that it's the length of paths traveled by light during a certain time interval. And that time interval is 1 over the speed of light. This definition effectively defines the speed of light to be this number, 299 million and some odd thousands of meters per second. That is the definition of the speed of light. And because of this universal relationship, that the wavelength is equal to the speed of light divided by the frequency of light, anytime you can measure the frequency of any light, you know its wavelength, and you've got a ruler. The beauty of this definition is that it doesn't matter if somebody makes a better laser. It doesn't matter if somebody invents a new way of measuring the frequency of light. And people did those things. The definition is still good. So we went from an artifact to an atomic constant of nature to a fundamental constant of nature, the speed of light. And this definition is brilliant and beautiful because we should never need to change it again, no matter how much our technology improves. This definition should be good. So let's pause once more and see if anyone has any questions, either about time or about length, before we go on to the next subject, which is going to be mass. So, any questions about length or about time?
Any questions from the audience? We have a couple of questions. I'll redirect them to you.
Excellent.
Is it possible to get a measurement of time that's more accurate than a part of 10 to the power of -16?
Dr. William, did you hear the question or can I repeat?
No, I think you'll have to repeat it.
The question is it possible to get the measurement of time to more accuracy than 10 to the power of -6, did you say?
Yes. Yes. So right now, the definition of time is limited to a few parts in 10 to the 16. Now, that's incredibly accurate. It's the most accurate thing that we can measure. But the fact is, and I hope to talk about this toward the end of my talk, we now have new technologies that have improved the measurement of time so that we can now do better than 1 part in 10 to the 18. That is absolutely astounding. If you started such a clock at the beginning of the universe, at the time of the Big Bang, which of course would not have been possible, but if you had such a clock at the time of the Big Bang, it would have gained or have lost less than 1 second by now, 14 billion years later. So I'll talk a little more about how those clocks work toward the end of my talk, but the answer is yes. We are continually improving the measurement of time. It's the thing we do best.
We have one more question. Yes, please. I'll take one from this.
In non-relativistic periods, basically when the speed faster than the speed of light, does that make the measurement of the meter change as well?
Measurement of
the meter.
Okay. When we go to the non-relative regime, will the measure of meter change? Is the second question.
Okay, when we go to what regime?
Like when it in non-relativistic areas.
Non-relativistic area.
Oh, non-relativistic, right. Okay, yeah. The definition of the meter as it was done in 1983, which is when the new definition, yes, 1983. This definition is formally independent of any theory like the theory of relativity. The reason why it's useful is because the theory of relativity tells us that the speed of light is independent of our motion relative to any other reference system. So regardless of what reference system you're in, this is the definition of length. Now, what relativity tells us is that different people will measure the same object to be different lengths depending upon how fast they're moving relative to that object. And so that means that given this definition, we will have this relativistic transformation. So what does it mean in practice? What it means in practice is this definition of length is applicable to whatever reference frame you're in. This is called proper length. So whatever reference you're in, this is your definition of length. I hope that's helpful.
Is it okay? Is it okay to take one more question at this point and save
Sure.
later?
Yeah.
What will be the question?
Is there any factor that will affect the wavelength or the speed of light, like gravity bends the light?
The question is there any possibility that
Any other extrinsic factor would affect the wavelength or the speed of light?
any other extrinsic factor affect the speed of light or the wavelength?
Well, yes. In general relativity, Einstein's theory of gravity, being close to an extremely dense mass, like a black hole, can distort space itself. And so the meaning of this definition becomes more ambiguous when we are in extreme situations where we have highly curved space-time. So it's best to think about this definition in flat space rather than in curved space-time. Einstein's theory, as far as we know, will give us a completely correct definition of how that curved space-time behaves and what we would measure. But in terms of the philosophical question of what does a meter or what does a second mean under these circumstances, well, again, we take the point of view that everything is local. But if you have extremely extreme conditions, as you might have near a black hole, then what is meant by local is perhaps somewhat ambiguous. And so we really should think about these things in flat space. Thanks for that question. That's a very insightful question.
Any more questions at this stage? Dr. William, it seems we are good.
Okay,
for
let's
now.
go on. So now this definition of the meter based on the speed of light is both brilliant and beautiful, in my opinion. Even more beautiful than the definition of the second, because it involves a truly fundamental constant of nature rather than something tied to a specific atom. In the year 2019, on the 20th of May, which, as I mentioned, is International Metrology Day. The reason that date is it's the anniversary of the signing of the International Treaty of the Meter, which fixed the metric system as the system of units for the entire world. On that date, we brought this same beauty, this same brilliance to the definition of the kilogram, and for that matter, to the ampere, the Kelvin, and the mole. And that is the revolution in the metric system that I've been talking about. So why was it necessary to do this, and how is it accomplished? The metric unit of mass is the kilogram, and the French revolutionaries in the 18th century decided they should have this new unit of mass, and that it should be based on the new unit of length, the meter. So they said that the new unit, the kilogram, was equal to the mass of 1 liter of water, and 1 liter of water is a cube that is 1/10 of a meter on a side. So this was the new unit of mass, the mass of a liter of water. It turns out that it's not that easy to determine exactly what the mass of a liter of water is. The water is not very dense, so there's air buoyancy. The water sticks to everything that it touches. It forms a meniscus so that it's hard to define exactly what the volume is. The density of water changes with temperature. So for all of these reasons, water is not the most convenient thing to use as a definition of mass. So the French revolutionaries did what the ancient Egyptians did when it came to length. They made an artifact. And here is that artifact. That little cylinder there is a platinum cylinder whose mass was made as close as possible to the mass of a liter of water as they could measure. And this, in the year 1799, became the standard of mass for the country of France. And in 1875, when the countries of the world agreed to adopt the metric system, they agreed to make a new standard of mass out of platinum iridium. This is illustrated here under these three glass jars. That standard of mass made as close as possible to the kilogram of the archives. That's called the International Prototype Kilogram. It's the last artifact. And here's the problem. We are in the 21st century. The unit of mass is an artifact, a piece of metal that was made in the 19th century, the International Prototype Kilogram. It's based on an object that was made in the 18th century. This is scandalous. If somebody left a fingerprint on the International Prototype Kilogram, it would mean that all of us would lose weight. That's not a tolerable situation. Now, nobody leaves fingerprints on the International Prototype Kilogram. It's handled very carefully. But in spite of all that care, it appears that the mass of the International Prototype Kilogram is changing. Here's a plot of the mass of the copies. Many copies were made at the same time, and the one that was closest to the mass of the international of the kilogram of the archives was chosen to be the International Prototype Kilogram. But all these other kilograms were made in a completely identical way at the same time as the International Prototype Kilogram, which is shown here with this big K. It doesn't change by definition, but look at all these other masses are changing by many micrograms over the period of a century. Now, when you see all of these copies changing in the same direction, it makes you think that the kilogram itself, that is the International Prototype Kilogram, must be changing relative to them. That's intolerable. We can't have a standard of mass that is changing, just as we couldn't have a standard of time that was changing. And so we needed to fix this situation. And we wanted to fix it using the same beautiful approach that was used for the meter. To define the meter, we defined the speed of light. To define the kilogram, we're going to use the most quintessentially quantum constant, namely Planck's constant. So to see how this works, let me first remind you of what surely is the most famous equation in all of history, E equals mc squared. What does that mean? It means that the energy of an object at rest is equal to the mass, the rest mass of that object, times the square of the speed of light. Okay, E equals mc squared. Here's another equation, not quite as famous, due to Planck, that the energy, well, it's really due to Einstein, that the energy of a photon, for example, a particle of light, is equal to Planck's constant times the frequency of the light. So if we have light, which in the 19th century was discovered to be a wave, and that means that it has a frequency, there's a frequency at which this wave oscillates. Einstein taught us that we should also think of that light as being a stream of particles, the way Newton imagined. So it's both a wave and a particle. This is the beginning of quantum mechanics. And the ratio between the energy of a single particle of light and its frequency, that ratio is given by what we call Planck's constant. So now I'm going to take this equation, E equals mc squared, and E equals hf, and combine them and solve for the mass. So it says the mass is equal to Planck's constant times the frequency divided by c squared. What does this equation mean? It means if I had an object, let's say an atomic nucleus, and it emitted a photon, a gamma ray, whose frequency I could measure, then if I define Planck's constant, h, take that, multiply it by the frequency, divide it by c squared. The speed of light is something I've already defined in order to define what we mean by a meter. So having newly defined Planck's constant, I will know what the change in mass of that nucleus is. Now, this idea is simply to illustrate how defining h can lead to a new kilogram. We're not actually going to be doing the experiment I described. We can and do, but not well enough. Instead, we're going to use Planck's constant, quantum physics, and laser cooling to measure the mass of a single atom. And it's the mass not in atomic mass units, but in kilograms. And then we're going to take that mass of a single atom and multiply it up many times to get a full kilogram. So here's how it works. Here's a cartoon of an atom. Typically, this is going to be an atom of rubidium. It might be cesium. And let's imagine that it's at rest in the ground state. Now, it's not very easy to get an atom at rest, but laser cooling allows us to make the temperature of these atoms to be on the order of nanodegrees above absolute zero. So they're effectively at rest. And we can account for the fact that they're not exactly at rest. And this atom is in its ground state. That means that the electrons in the atom are in the lowest energy state that's possible for those atoms. Now we shine in a laser, and that laser is a stream of photons, and one of those photons is absorbed by the rubidium atom. So the electron goes from the ground state into the excited state. But that photon also carries momentum. And we know how much momentum it is. It's Planck's constant divided by the wavelength. Now remember, we're going to define Planck's constant, and we can measure the wavelength of the light very accurately. All we need to do is measure its frequency, and we know its wavelength. So we know the momentum of the photon. Because of conservation of momentum, when the atom absorbs the photon, it recoils, it starts to move, and using conservation of momentum, we can calculate how fast it's moving. It's moving Planck's constant divided by the mass of the atom in kilograms and the wavelength of the light. That turns out to be a few millimeters per second. And it turns out we can measure that velocity extremely accurately. And once we've measured that velocity, then we know the mass of the atom. That mass is equal to Planck's constant, which we now have defined, divided by the velocity, which we're going to measure, and the wavelength, which we're also going to measure by measuring the frequency. So that means that we now know what the mass of, say, a rubidium atom is in kilograms, something that we've never been able to do with that kind of accuracy before. And this was made possible by a lot of the things that were done in my group at NIST. And this is a picture from some years ago of the entire group. Students from all over the world come to study in our group and to work on understanding some of the most beautiful issues about how the world works. We developed many of the techniques that made this determination of an atom's mass possible. We haven't been doing it ourselves, but we made it possible for other people to do it. And along the way, we made some unexpected new discoveries. We made the accidental discovery that it's possible to cool atoms, in some cases, to temperatures more than 100 times colder than what the theory thought was possible. This is one of the most exciting things that can happen in the life of a scientist, to discover something completely unexpected, to discover something completely opposite to what most people had thought was the case. And this happens all the time in science. And it's one of the things that makes science such an exciting field to work in. Well, anyway, once knowing what the mass of a rubidium atom is, we multiply it up using a technique involving this sphere of silicon. So silicon, the material that's used to make computer chips, for example, can be made in large chunks as a perfect crystal. This is a perfect crystal of silicon that's been machined and shaped into a perfect sphere. We measure the distance between the silicon atoms using X-rays in this perfect crystal. And that distance is the same throughout the entire crystal, which is what we mean by making it a perfect crystal. We measure the size of this sphere, and that means we know how many silicon atoms are in there. We can measure the ratio of the mass of the silicon atom to the rubidium atom. And now we know what the mass of this sphere is in kilograms. This is not an artifact. This is a kilogram that can be made by anybody who had the right techniques. It's not like the International Prototype Kilogram, which is defined to be a kilogram. This is an object that is made to be a kilogram using our new definition of Planck's constant. That's not the only way to get mass from Planck's constant. This gentleman, Brian Kibble, at the National Physical Laboratory in England, in Teddington, outside of London, invented a device which we now know as a Kibble balance. And this gives us another route to determining the kilogram using electrical constants, where this constant 2e over h, the charge of the electron divided by Planck's constant, gives us a measure of voltage. And this constant, h over e squared, gives us a measure of resistance. We can use these things, these electrical quantities, to produce a force that, once we know the acceleration of gravity, gives us a mass. And in fact, that's why I went to NIST in 1978 to start to work on Kibble's idea. And finally, in the year 2019, it came to fruition in redefining the kilogram. So I'm not going to go into the details of how that is done, but you can ask about it if you want later. But I want to stop here and see if you have any questions about mass, or for that matter, if you have any questions about time or about length.
We have one question from the audience.
It would be possible that mechanism of the cesium clock, like how does it work?
What's the question?
How does the cesium clock work?
One of them in the live audience is interested in how does the cesium clock work?
Yeah, okay. Let me give you a little bit more detail about how that works, because obviously I glossed over it rather quickly. So the idea is that there are certain energy levels in every atom, including the cesium atom. And I'm just trying to see if I have any slides about that. But in the case of the cesium, I don't know if you can see me, but I'm holding up my my two hands. The cesium atom has a nucleus. Okay, so that my thumb is representing the spin axis of that nucleus. Okay, so that nucleus is a charged object. It's spinning. It creates a magnetic field. Cesium is what we call an alkali atom. It's got one valence electron. So my other thumb represents that other valence electron. It's a charged object, and it's spinning as well. So it generates a magnetic field. The electron feels the magnetic field of the nucleus. And if the electron changes its orientation relative to the nucleus, that's going to change its energy. Just like if you had a compass needle and you wanted to move the compass needle from pointing north to pointing south, you'd have to expend a certain amount of energy to do that. Well, that's the same thing with the electron. If I want to turn it from here to here, I have to expend energy. Now, how do I do that? I shine in microwaves at about 9 gigahertz. And when the energy of those microwave photons exactly matches the energy difference between this orientation of the electron and that orientation of the electron, then the electron will change its orientation. You've got to match the energy of the change of the electron configuration to frequency of the light, and that's what's called resonance, and that will cause the electron to flip its spin, and you can tell whether the electron flipped its spin. Here is a kind of a cartoon version of that. Okay, so looking at the screen now, you see here's the cartoon of the nucleus. There's the of the atom. There's the nucleus. There's the electron. If we shine in microwaves and they exactly match, then the electron will flip its spin. And if they don't match, if the frequency of the microwaves don't match, it won't flip its spin. And so we can tell the difference between having the right frequency and having the wrong frequency. Now, what we've done in 1967 is define that frequency to be this number. And that's the way in which we, in the case of time, define the unit of time by defining a constant of nature, namely this this frequency of what's called a hyperfine transition. Now, this is the oversimplified version of an atomic clock. This is the more detailed description of the atomic clock, but unless you really want the details, I won't go into that. But anyway, there's the picture again of the newest of the atomic clock, not the newest, the first of the atomic clocks. Here's a picture of the newest of the atomic clocks. The cesium atoms are cooled down to 1 microdegree above absolute zero, launched up in this tower. They come back down after about a second, and it's these clocks that are good to a few parts in 10 to the 16th. So I hope that has answered that question. A little bit of a long answer.
Thank you, Dr. William. Maybe in the interest of time, we'll let you finish the slides and have last minutes for questions.
Okay, so now I have to go back to where I was. Okay, so now we have these two ways of measuring mass. We can do it with the measuring the mass of a single atom and then making this perfect silicon sphere. We can use this electromechanical device that Brian Kibble invented. And so people all over the world, using both of these techniques, compared their results. And when all of the laboratories around the world agreed within a few parts in 10 to the 8th, which is smaller than the amount by which these kilograms were drifting around, when they all agreed on their measurements, then the international community got together and voted to change the definition of the kilogram to be based on a fixed value of Planck's constant. And we met in Versailles, outside of Paris, in 2018 to take this vote of the international community. 60 countries who are the signers of the International Treaty of the Meter voted unanimously to adopt this new definition. And after that vote was taken, this video was shown.
It took more than 140 years.
Groundbreaking science.
And the agreement from the world scientific community. At times, it seemed
Impossible.
accurate.
Precise measurements.
Anytime.
Anywhere. But
We did it. Ce l'abbiamo fatta. Wir haben es geschafft. Lo logramos.
Neyse Boli.
Biz bundan ayrı olduk. Welkom daar.
Dus wonderzalig. Het is ons gelukt.
Unterstellen.
Wie gjorde det?
Amerika, ja.
My jsme to učinili.
Dokázali jsme to.
Congratulations. Candidate. Felicitaciones.
Mazal Congratulazioni.
State rally lavorisce.
Selamat sukses. Parabéns. Ongera. Omedetou.
Anguida.
Oneksolo. Mabruk.
Kapai.
Aiko.
Félicitations. Congratulations.
I still become emotional when I see that video, because to think that 60 different countries could unanimously agree on something, and this was not an easy agreement. There were very strong disagreements about how this change in our measurement system should be made. But 60 countries finally unanimously agreed. And the fact that that was possible gives me hope that perhaps it may be possible for us to resolve international differences in such a peaceful and rational way in the future. Well, there's more to the story. The definition of the ampere used to be that the ampere was that current which in two infinitely long straight wires 1 meter apart would produce a force of 2 times 10 to the minus 7 newtons per meter. Today, the definition of the ampere is based on defining the charge of an electron. So an ampere is just this number, the charge of the electron. The inverse of that number of electrons per second, is the definition of the ampere. The Kelvin, the unit of temperature, used to be 1/273.16 of the triple point of water. Now we've defined the Kelvin by defining the Boltzmann constant. The kinetic energy of thermal motion of an atom at a certain temperature is given by that temperature times the Boltzmann constant. So we're now defining temperature in an atomic and microscopic way in terms of the energy of the atomic constituents of the matter. The mole, the amount of substance, used to be the amount of substance that has a number of elementary entities equal to the number of carbon-12 atoms in 12 grams of carbon-12. Today, it's simply a number, the Avogadro number. We've now defined Avogadro's number to be this number. So now the French Revolution brought us the metric system. Meters as length, kilograms as mass, and eventually seconds and amperes and kelvins and all the rest. The International Treaty of the Meter brought us an international agreement about units, that the entire world adopts the metric system. And on the 20th of May, 2019, the anniversary of the signing of the International Treaty of the Meter, we had the biggest revolution in measurement since the French Revolution that fixed all of the base units in terms of the constants of nature. It appears that we have finally realized the dream of the French revolutionaries, realized this dream using quantum mechanics to have a system of units that is good for all time and for all people, except for time itself. Because time, the definition of time, is still tied to a specific atom, cesium, rather than a fundamental constant. And we now need a new definition of the second, because optical frequency standards, not microwaves, the way cesium is, but optical frequencies are making better clocks. Anna Maria Ray and Junyi take strontium atoms, put them in what we call an optical lattice, and measure the frequency of an electronic transition with an accuracy of 2 times 10 to the minus 18. Dave Wineland takes a single trapped aluminum ion and measures it to 9 times 10 to the minus 19. And just last week, the team in Boulder with Junyi has achieved 8 times 10 to the minus 19 for their measurement of strontium. These measurements are getting better and better all the time. And one of these atoms, or maybe a group of them, will be chosen to define the new second. So what will happen for the future of time? We're working on it right now, trying to decide how to redefine the second. Only time will tell, but for sure, it's going to be quantum. Thanks very much.
Thank you so much, Dr. William. Any final questions? We have a couple more minutes.
And if you want I'm perfectly happy to answer questions about my career, about laser cooling, whatever you want.
Can I ask a quick question on, is there anything you are focusing at the moment?
Well, I'm part of an international committee that is trying to decide how to redefine the second. In our own laboratories, we're working on using cold atoms as a way of simulating the quantum mechanical behavior of materials. So it turns out that it's too complicated to calculate using quantum mechanics how even simple models of materials work. And so we're trying to see if we can gain insight by using cold atoms as a kind of a stand-in for quantum materials. And so we're working on that, trying to understand things like superconductivity and magnetism using the cold atoms that we originally developed in order to make better timekeeping.
Thank you so much, Dr. William. We really look forward to read your works more. I think
we have at least two more minutes we have.
I'll try to reiterate it. Oh, yes, you can come here. It will be better.
Dr. William, can you hear me?
You go ahead. Yes, go ahead.
Yeah. So in science, we are always limited by what we don't know. So there was a paradigm change from knowing standards around ourselves to standards around quantum. Is there a next paradigm shift, even conceptually in view, many years out from quantum? Or you see for the foreseeable future, quantum will define the limits of what we know?
Well, that's an excellent question. I would say that for the foreseeable future, I expect the current definitions, except for the definition of time, to be sufficient. But I expect that we will see changes, probably not in my lifetime. Right now, we know that Einstein's theory of gravity is not consistent with our understanding of quantum mechanics. It's one of the great challenges of modern physics, is how to bring these two great theories together. We don't know how to do that. When that is done, and I have confidence that it will be done, but probably not in my lifetime, when that is done, it will probably change the way we think about measurement. Whether it changes it enough that we need to change our definitions remains to be seen. We can only realize the new definitions of mass to a part in 10 to the 8th. We can realize new definitions of time to a part in 10 to the 18. So something that changes our conception of time is going to be much more sensitive to changes in our understanding of physics than something that changes our conception of mass.
Thank you. Thanks.
Thank you so much, Dr. William. We have one quick question, if you're okay.
Yes.
A very quick question, please.
I was wondering, so when you mentioned the different atoms from the aluminium and plutonium being used in quantum, what qualifies an element?
I lost you.
So you mentioned different elements to be used. What can qualify and specific elements to be used?
The question is, what qualifies an atom or a material to be qualified for timekeeping?
Yes. Well, it turns that's an excellent question, and it has a rather long answer, unfortunately. Today, it should be an atom that is easily laser cooled. It should be one that has a transition that is extremely narrow. So that means that the excited state has to have a very long lifetime. It has to be something that is easy to use in the laboratory. It needs to be something where both the clock transition frequency and the laser cooling transition frequency are correspond to lasers that we can easily get and easily operate. So there's a lot of different criteria that go into what makes a good atom, and the panoply of possible atoms from which we're choosing today, the choice is so difficult because some of the atoms are better in some respects and other atoms are better in other respects. And we need to choose between these things for which there's no clear choice.
Thank you so much, Dr. William. I think I muted your well-earned applaud lastly, so we'll go ahead for one last thank you for Dr. William. Thank you so much.
It's a pleasure.